Welcome to the channel VLSI Point. We have created a new playlist called Digital Electronics. In this playlist, we are going to solve digital electronics questions. Those are helpful to you for preparing GATE exam as well as to crack the interviews of various semiconductor companies. Without further delay, let's get started. Question number 1. Minimum number of 2 input NAND gates that are required to implement the function F equals to X bar plus Y bar into Z plus W. Let's see the options. A 3, B 4, C 5, D 6. So basically we have to put the function in a such a way that we can directly implement using 2 input NAND gates, and that should be the minimum number. So we will solve this. We have written down the function F equals to X bar plus Y bar into Z plus W. Let's multiply with Z and W. Our function become X bar plus Y bar into Z plus X bar plus Y bar into W. We are just keeping X bar plus Y bar is A in the equation, and our equation becomes F equals to AZ plus AW. But to implement this function in the form of NAND gate, we have to use De Morgan's law. Okay, you can see here AZ plus AW we can write in the form of AZ bar into AW bar whole bar. It's like A plus B we can write in A bar NAND gate. Okay, again A into Z whole bar we required second, A into W whole bar we required third, and you can consider AZ bar as Z and AW bar as something W. So for to implement these two we require fourth NAND gate. Okay, so there are for this equation we should require total 4 NAND gates, 1, 2, 3 and this 4. So our answer, you can see here answer is 4, and you can see the circuit diagram. So X into Y whole bar we have taken as A. Similarly A into Z AZ bar we are taking another NAND gate, W into A bar another NAND gate, and this is the last NAND gate which is fourth NAND gate. So answer is B. Let's move to question number 2. Question number 2 is for the identity AB plus A bar C plus BC is equals to AB plus A bar C, the dual form is. So below are the options. Basically before starting this we should know what's exactly duality is. So whenever you are getting the function, you have to replace 0 with 1 and OR with AND and vice versa. Okay, in this is a function they have provided AB plus A bar C plus BC is equals to AB plus A bar C. Here as we mentioned here, whatever the into sign is there we have to replace with plus sign is we have to replace with AND, that is multiplication. So AB becomes A plus B, A bar C becomes A bar plus C, BC becomes B plus C. All this addition signs we have to replace with multiplication. Next same we are doing after this, AB, A plus B, A bar C is nothing but A bar plus C. Okay, so answer is A. You can see this is the answer. Let's move to third question. The Boolean function A plus B is a reduced form of AB plus BC, A plus B into A plus C, A bar B plus AB bar C, or A plus C into B. So basically we have to solve all these equations they have provided in the options, and we have to see which is the option providing the function A plus BC. Okay, so we will take each and every option, we will try to simplify that. If it is matching with A plus BC, that's your answer. Those are the options I have taken, A, B, C and D. What is A? A is nothing but AB plus BC. So here you can directly simplify by taking B as common. If you take common B, you will get equation as B into A plus C. Let's go to second option. Second option is A plus B into A plus C. So you can multiply, simplifying this, you will get AA plus AC plus BA plus BC. Then you just take A plus AC plus BA plus BC. Okay, now from this equation you can take A as common. If you take A as common, it's nothing but 1 plus C. If you take BA plus BC, you can take B as B common as well. Okay, before that we should know A into is nothing but A. For example, if you are multiplying 1 with 1, it is 1. If you are multiplying 0 with 0, it is 0. Okay, so that's the reason we have taken A as A. Okay, so here 1 plus C we are is nothing but 1. So if you are adding any variable with 1, it will give 1. Okay, so A into 1 again A. So BA we are taking as it is, BC as we are taking as it is. Okay, let's take A outside. You will get 1 plus B in these two terms, and here BC is as it is. So 1 plus B again it is 1. A into 1 is A. So equation becomes A plus BC. And if you see option C and D, we can't simplify further because they are already reduced form. So A bar B plus AB bar C, there is nothing you can't take in common, and D also is already in the reduced form. Okay, so what is our answer? Our answer is option B. Let's get to question number 4. Minimum number of 2 input NAND gates required to implement the Boolean function Z equal to AB bar into C, assuming that we just have A, B and C variable. Okay, let's see the option. 2, 3, 5 or 6. Okay, so they have provided function Z equal to AB bar C. Here we don't have B bar. So whatever the signal we have, they are in the form of A, B or C. Okay, let's see how we can solve this. We are just noting the function y equal to A into B bar into C. And as we have discussed last time also, to simplify further, we are just taking bar, 2 bars. For example, if you have function A is nothing but A bar whole bar, because bar will get cancelled. To simplify, we are just taking 2 bars. Simplifying further, you will get AB bar as a one term, you consider C as another term. So AB bar whole bar plus C bar and the complete whole bar according to De Morgan's law. Again simplifying further, A B bar whole bar, this term we can simplify as A bar into B bar whole bar. Okay, is nothing but B, and C bar as it is. Okay, here you have A bar and C bar in addition, so you can take A into C whole bar. Okay, so basically we are just playing with the De Morgan's law over here, and you can clearly see for A into C whole bar. Okay, we require one NAND gate. Second NAND gate is this for the bar we are taking. Okay, now let's say for A into C bar plus B, we require one OR gate, right? To just simplify, just consider A into C whole bar as a variable Q. So for Q plus B whole bar, that is nothing but the NOR gate. But if you consider Q plus B, it is OR gate. So to simplify this, we require 3 NAND gates. Fourth NAND gate is for the A into C bar, and this is complete whole bar is a fifth NAND gate. So total 1, second, and yeah, those 3 for OR gate. So total 5 NAND gates are required. So our answer is C, 5 NAND gates. Let's go to question number 5. For the circuit shown below, the output F is given by. So we have some circuit here. There are few XOR gates over here. We have to solve this circuit. Okay. So input is nothing but X they have given. So output is F. We have to solve whether it is 1, 0, X or X bar. Let's get started. Okay. So basically we have 3 OR gates here. We will solve one by one. So output of first XOR. Output 1 is nothing but X, XOR X. So you can refer the right side truth table. This is a truth table for XOR gate. If you have 0, 0, it is 0, 0, 1, 1, 1, 0, 1 and 1, 1, 0. So if you have same inputs to the XOR gate, we are getting 0. Okay. So clearly from the first XOR gate output is 0. Let's see how the output of second XOR gates will be. So output of second XOR gate is nothing but output of first XOR gate and the X. You can see over, right? This is second XOR. First input is from this XOR and second is nothing but X. So 0 XOR X is nothing but X. You can see over. If 0 is there, whatever the second input is coming as output. If it is 0, it is coming 0. If it is 1, it is coming 1. Okay. So X XOR 0, nothing but X. So output of third XOR is nothing but output 2 into X, output 2 XOR with X. Output 2 is nothing but X. So XX becomes 0. So output of third XOR gate is 0. So option B is the correct answer. Let's go to question number 6. Question is, a ring oscillator consisting of 5 inverters is running at a frequency of 1 megahertz. The propagation delay per gate is. So what are the things given in the question? Let's see. We have 5 inverters in a ring oscillator. They have given a frequency as 1 megahertz and we have to calculate the propagation delay of each gate. Okay. Before that, we should know what is the frequency of a ring oscillator. So it is nothing but 1 upon 2 into number of inverters you have into time period of each inverter. Okay, but we have to calculate T inverters instead of F. So T inverter is nothing but 1 upon 2 into N into F. Okay, is nothing but N is they have given 5 and frequency given as 10 raised to the power 6 hertz, that is 1 megahertz. So by solving you will get T as 100 nanoseconds. Okay, so answer is 100 nanoseconds. You have to remember this formula, and sometimes they will give T inverter, you have to calculate F, or sometimes they will give F and we have to calculate T inverter. Let's go to question number 7. So Boolean expression for the output of XNOR, that is equivalence logic gate with input A and B is. Okay, so they have given some options: AB bar plus A bar B, A bar B bar plus AB, and those C and D options. Okay, so what we have to do, we have to solve each and every equation and we have to see whether it is matching with XNOR or not. Before going to XNOR, it is nothing but Y equals to A bar B bar plus AB. So this is a XNOR function. If you see the truth table of XNOR function, it is like 001, 010, 100, 111. For inputs which are matching, it will flag output as 1. If it is different like 10 or 01, it will give 0. So if you see AB bar plus A bar B, this is not XNOR, this is a XOR function. Okay, so option A is not the answer. We will see B, S. A bar B bar plus AB. This is the XNOR function, we know. So B is correct option, but again we have to simplify C and D to check whether those are the correct options or not. So C is A bar B, A bar plus B, A plus B bar. So we just multiply with the first bracket with second, we will get this particular term. And in this A bar A, if you see 1 into 0 or 0 into 1 is nothing but 0. Okay, so A bar A and B bar, it will get cancelled. So C option is nothing but A bar B bar plus B A or AB. So this is nothing but our option for the XNOR. Okay, this is the correct option. In the D, if you simplify further, A bar A will get cancelled, B bar B will get cancelled as in the option C, but A bar B plus B bar A is nothing but XOR. So basically in this question, A and D for XOR and B and C for XNOR. So we have multiple answers, B and C. Okay, we'll move to question number 8. For the logic circuit shown in figure, the output is equals to. You can see this is a few of the gates they have taken. They have taken a few NAND gates, they have taken OR gates, and for this circuit we have to see what's the output, and they have provided few options. Okay, so to simplify further, what we will do, we will just take we will number all these gates so that it will be the better approach. Okay, just I am redrawing the circuit over here. 1, 2, 3 and 5 are nothing but NAND gates, 4 and 6 are the OR gates. So here at the end we have 3 input OR gate. Okay, so we will go from this like this approach. Y is nothing but, that is output of OR gate is nothing but whatever the output of these 3, 4 and 5, we will just add it. Nothing but Y equal to 3 plus 4 plus 5. So once we get what is 3, what is 4 and what is 5, we can directly add them and that will be our final answer. Okay, so we'll start one by one. So I have taken, this is the output of the gates we have. You can see 1 is nothing but this gate. So what is the output? A into B bar, A into B bar. Similarly for 2 is here, B into C bar, B into C bar. Third gate, just it is a inverter, just they have taken A bar because the terminals of those two NAND gates are shorted, so it's nothing but A bar. 3 is A bar, 4 is AB bar plus BC bar. You can see whatever this output of first NAND gate and second NAND gate, just we are doing addition operation over. And for 5, it is nothing but C bar. So now 3 is ready, 4 is ready, and 5 is ready. Okay. But we have to just simplify AB bar and BC bar. Maybe we will get some reduced form of this. Okay, so AB bar is nothing but A bar plus B bar according to De Morgan's law. BC bar is nothing but B bar plus C bar, and we know B bar plus B bar. If you are, one of the terms is repeating, it is nothing but only one term. Let's say here B bar is there, again B bar is repeating, so it is nothing but B bar. Okay, so 4 is become A bar plus B bar plus C bar. So if we add 3, this 4 and 5, we will get A bar plus, this is 4, A bar, B bar, C bar, and this is C bar. So as we discussed, C bar is nothing but C bar, A bar is nothing but A bar. So our final answer is Y equals to A bar plus B bar into plus C bar. So our answer B, A bar plus B bar plus C bar. Okay, we'll go to question number 9. Question number 9 is the minimum number of NAND gates required to implement the Boolean function A plus AB bar plus AB bar C is equals to. Let's see what's the options. 0, 1, 4 and 7. So we have to solve this question in such a way. First, just simplify this function, whatever they have given. Second, just see how we can solve using minimum number of NAND gates. Okay, previously also we have solved these questions, one question of this type. Okay, so we will see how we can go with this. Clearly, it is, see, we can see here A is common in Y, all the three terms. If you take A outside, it is 1 plus B bar plus B bar C. Okay, so we know 1 plus anything, right? It is nothing but 1. So if we are adding 1 plus any expression, whether it is B bar plus B bar C or whatever the function, the output will be 1. So here in the bracket you can see it is 1 plus B bar plus B bar C. So there is no need to solve again. I mean B bar taking common and 1 plus C. No, simply 1 plus anything, it's 1. Okay. So here Y is nothing but A into this complete term 1. So we are reduce the equation in the form of just Y equals to A. Okay. So you know A, just you have to implement this using NAND gates. There is no need of NAND gates. Simply if you have input A, just take a wire. Okay, so there is no need of NAND gates for this. So answer A, 0. So we don't require any NAND gate. Okay, so let's go to question number 10. The output of logic gate in figure is, they have given XNOR gate. One of the inputs is connected to ground, another is A, and output they have taken as F. Okay, let's see. So we know, sorry, by mistake here XOR, it is XNOR. So XNOR output, okay, is nothing but Y equals to A bar B bar plus AB. Okay, but you know B is nothing but 0 over here. So A bar into 0 bar plus A into 0. So you know A into 0 is 0, 0 bar is 1. So Y is nothing but A bar. So output of this function, that is F, is nothing but A bar. Okay, answer C, A bar. Let's go to question number 11. For the logic circuit shown in a figure, the required input condition ABC to make the output X as 1. Okay, let's see the options. A, B, C, D. Those are the options 101, 001, 111 and 011. So let's see what the question basically telling is. So these are the combinations of A, B and C. Okay, so for example, in the option A is 1, B is 0 and C is 1. If we keep those options as inputs in this particular circuit, so the output we should get as 1. Okay, so which of the combinations is giving output 1, that we have to find out. Okay, so let's solve this question. As usual, I am just nomenclating this particular gates as 1, 2 and 3. So X is here 3 input AND gate, and output of 3 input AND gate is nothing but OP1 into OP2 into C. C is directly we are connecting from here. Okay, so OP1 is nothing but output of this XOR. OP2 is nothing but output of this XNOR. Okay, and X is our final output. X is equals to OP1 into OP2 into C. So let's solve for OP1 and OP2. Okay. So we know for OP1 to be 1, if we want this one, right? Also we want OP2 1 and also we want C1. So that is the condition for the AND gate. If all the inputs are 1, we will get output as 1. Okay. So let's see for OP1 should be, if you want OP1 as 1, we know A and B should be different. Okay, because this is XOR gate. We have seen the truth table of XOR gate. Okay, so if we have 0 0, it is 0. If it is 1 1, it is 0. We want 1. So A and B should be the different. Okay, so what are the possibilities? If A is 1, B should 0. If B is 0, B is 1, A should 0. Okay, vice versa. So 1 0 or 0 1 are the possibilities for A and B. And we want C must 1. Okay. So I am just taking this as equation 1 or point number 1, that A and B should be different. For output 2, if you want 1, right, B and C should be same. So for the XNOR, if you see here, if this is equivalence gate. So if you see 0 0, it is giving 1 output. If it is 1 1 inputs, it is giving 1. Okay, so either it is 0 0 or it is 1 1. But in this case, C is 1 already, we told, right? So this 0 0 option get cancelled. If C is 1, we want B obviously 1. So we want B as 1. Okay. If you see question number 1, if you want B1, means A should be 0. So we want A0, then we want B1, and obviously we want C1. So the correct combination ABC, which will give the output 1 for this particular diagram, is nothing but 0 1 1. So 0 1 1 is the option D. So the answer for this is option D. Okay. Let's move to the question number 12. For the ring oscillator shown in the figure, the propagation delay of each inverter is 100 picosecond. What is the fundamental frequency of the oscillator output? We have already seen such kind of question, but here we want frequency. Okay. So we'll see options. They are provided in the megahertz and gigahertz form. 100 megahertz, 100 megahertz, 10 megahertz, 100 megahertz, 1 gigahertz, 2 gigahertz. Let's see how we can solve. As we know, frequency is nothing but 1 upon 2 into n into T inverter. N is number of the inverters and T is nothing but time of each inverter. Propagation delay. You can see here in the ring oscillator, odd number of inverters are there. There are total 5 inverters. Okay. So we can, after solving, we will get frequency as 1 gigahertz. Okay, just this is a simplification kind of thing. So fundamental frequency of the oscillator output is nothing but 1 gigahertz. Answer C. Okay, moving to our question number 13. The output Y in the circuit below is always 1 when. So this is a circuit. Okay, so the output Y is at the end of this particular NAND gate. So we have a couple of options over here. Okay, so what the question is telling. So the output Y, okay, in the circuit is always 1. So we want this 1. So what are the possibilities of P, Q and R? For example, in question A, it is saying 2 or more of inputs P, Q and R are 0. Okay, so option number A is telling out of this P, Q and R, at least 2 should be 0. Or at least 2 should be 0 means minimum either it is PQ or QR or PR, or all can be 0. So such options they have given. Let's simplify the circuit and we will check the options. We'll go by reverse approach. As usual, I am just renaming this gates 1, 2, 3, 4, 5, 6. Total 6 gates are there. So 6th is a NAND gate. Okay. So if you want this one, at least A or B should be 0. So you can see here truth table of NAND gate. These are the 3 combinations where we have output 1, 0, 0, 0, 1 or 1, 0. It's clearly seeing that we want at least it should be 0. So for this NAND gate output 1, we want either B or A or both as 0. So at least 1 should be 0. Okay. So for A, if we want to 0, P and R should be 1. You can see here. If one this is 0, so obviously P and R should be 1. So we have P and R as 1. That's a compulsory possibility. Next, for B0, Okay, so we'll see. For B0, C should be 1 as it is nothing but inverter. For C1, D or E should be 0. Okay, so here we have D and E. So D or E should be 0. Okay, as usual, as we discussed for this gate. As usual, as we discussed for this gate. Okay, for D is equals to 0 or for E equals to 0, both PQ and QR should be 1. Okay, so we want P and Q both 1 here, or we want Q and R both 1 here to get our desired output at C level. Okay, so you can see here from the equation number 1, what we are telling is we want P and R both should be 1, and here we are saying either we want P and Q1 or Q and R should be 1. Okay, but from equation 1 and 2 it is clear that any of two inputs should be 1. Either P and R should be 1, or P and Q should be 1, or Q and R should be 1. Okay, so it's clearly we can predict that. Okay, we want at least any of two input should be 1. So option B is the answer. Two or more inputs of P, Q and R is nothing but 1. Let's go to question number 14. For the output F to be 1 in the logic circuit shown, the input combination should be. So below is the diagram they have provided. We will see the options. A, B, C, D, those are the options. The combinations are 1, 1, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, so we want output F should be 1, but for only one of these combinations of A and B and C, the output should be 1. So we will see how we can solve this question. Yeah, you can see I have just named this first XOR as 1, XNOR as 2, and last XNOR as 3. Okay, so final output is nothing but XNOR of 3 inputs. Okay, so what are those inputs? First one is OP1. OP1 is nothing but XOR of A and B. Second is OP2. OP2 is nothing but XNOR of A and B. And C, it is as it is. Okay, so the equation F becomes OP1 XNOR with OP2 XNOR with C. Okay, so let's find out OP1, OP2. Okay, at the left hand side I have written truth table for 3 input XNOR gates. These are the combination of inputs, and this blue shade you can see the output. For example, if the 3 inputs of XNOR are 0, 0, 0, you will get output 1. Like that I have written for all the above combinations. So we can see our options. So if A, B, C are 1, 1, 0, we have OP1. OP1 is nothing but XOR of A and B. XOR of 1 and 1 is 0. So OPN will be 0. Similarly for OP2, it is XNOR of A and B. So for 1 and 1, it is 1. Okay. Similarly, C is as it is. For example, if we see this 0, 1, 0 as 3 inputs to the XNOR, you will find out here 0, 1, 0 output is 0. So our F output is 0. Similarly, we can do for 1, 0, 0, 0, 1, 0 and 0, 0, 1. Let's see for 0, 0, 1. OP1 becomes 0 XOR 0, 0. OP2 becomes 0 XNOR with 0, it is 1. And C as it is 1. So the combination of 0, 1 and 1, from the truth table it is clear that output F is 1. So answer is A as 0, B as 0 and C as 1. Let's see in which option it is. It is in option D. So our answer is answer D. Okay, this is about this playlist. Thank you so much for watching this video. Please like, comment and subscribe to the channel VLSI Point. Add your comments if you have any doubts regarding this first playlist of digital electronics. Thank you.